Hello and welcome to Learn Data. It's great to have you on this channel. In our discussion with Least Angle Regression, in this video, we'll look at the implementation of Lars, Lars path, LassoLars, and Lasso path. We'll also do some comparisons with Ridge path. So let's get into Jupyter Notebook and look at how we can code. So here I've imported these libraries: NumPy, datasets, linear model, metrics, a train, test, split, and matplotlib for plotting. And these are the versions I'm using. For data, we'll use the diabetes dataset that is in Scikit-learn, because that's also the dataset used in the paper that was published, which was referenced in the previous video in the slides. So we'll import it in two ways. So first is datasets dot load underscore diabetes, and here if we look at data.dscr, we can see how many features are there and what they are. So these are the features. There are 10 numeric features, so these are the features that we will be using. And then there will be one target picture. 11 column is the target. So based on that, we'll use this data, and secondly I'll import the same data set by a different method. So that is creating x and y. So maybe small x small y is equal to data sets dot load underscore diabetes and return xy, a capital X underscore small y is equal to true. So we do not get we get all the data in x and y here, and here we can do the train test split. So x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split. And here we can specify data dot target. Okay. And the data sets, the reason why I've done this in two ways is because you'll see sometimes we'll use this particular xy, sometimes we'll use this xtrain. So the very first implementation we'll look at is using Lars, and for that we'll create the variable reg is equal to linear underscore model dot LARS capital L and open close parentheses, and then we specify reg dot fit, and here we'll specify x train, y train, and then we can get the coefficients of this. So x t is equal to reg dot coef, and if we print these, let's see, coef, and we can print it on a new line t, and so these are the coefficients. Now we can predict. So y underscore pred is equal to reg dot predict x test. We'll use prediction based on the test dataset, and we'll calculate the MSE. MSE is equal to matrix dot mean underscore squared underscore error, and here we'll use y underscore test, y underscore pred, and we can print MSE, and this is right here. So we get a very large value of MSE, which is around 3000. And that's the basic implementation of Lars. We can also look at other attributes. So to look at what attributes are there, we can see in the help. And to get the help, we can type linear underscore model dot Lars question mark. And when we run that cell, here we can see that these are the parameters. Then these are those descriptions for those. And here are the attributes. And within this, we use the coef underscore up here to print the coefficients. Additionally, we can get coef underscore path underscore to get the list of coefficients, arrays of coefficients. And the shape is n features by n alphas plus 1. So now if we want to plot those, we can do that. So let's say print, I'm going to put that there, and then we can print. Uh, let's get the C. The values for coefficient C is equal to reg.coef underscore path underscore. Now, if we print the C dot shape, we can see that we have 10 features right here, and then we have 10 alphas and plus 1. So we can use this information to plot the regression, the coefficients. So to do that, what we can do is, let's type in new cell, see sum. So what I'm going to be doing now is getting the sum for alphas. So for different when not the sum for alphas, but whenever a particular alpha was used, there will be a value of coefficients associated for that alpha. So b1, b2, b3 for one alpha, then b1, b2, b3 for second alpha, and so on. So we can get the sum, and that will be the x-axis. So c sum is equal to, you're getting the absolute sum, so abs of c and np dot sum, and this would be along the axis is equal to, because the features are all on are as rows and the columns are alphas, so we'll get the axis as 0. And when we look at the c sum dot shape, we get 11. So total of parameter value for a particular alpha, those are there. Now we can use that to plot. So plt dot plot c sum and c. Now this will give an error. That is because the shapes do not match, and therefore we need to flip this particular matrix. It is 10 by 11, well, so we'll flip it to 11 by 10, and then we can get this particular plot. So this is the uh, uh, this shows the path of the coefficients, how they evolve. Let's add the title there. So this is for LARS, least angle regression, and we can also add dotted lines that correspond to this particular summed up values that we have. So just to show, we can do if you do a scatter. Okay, the scatter won't work in this case because we need only one value right there. So this is how the scatter looks like. These are the points and the line. When you use plot here, we are connecting them by a straight line. And here if we type y min y max is equal to plt dot y limit, the y limit, so limit of y axis, we can plot plt dot, we are plotting vertical lines using this the values in this particular array c sum. So these values, and here we specify y min, y max, and we can specify the line style as dotted, and we'll specify the alpha value. So this alpha is completely different. It has nothing to do with the alpha we have been talking about. This is just to adjust the transparency of the lines. And as you can see, they are exactly, the dots are exactly where the V lines are. And another point I want to show is how this particular scatter plot looks when we use the plot. So that's the line, and essentially if we remove that line, this is the plot. So if we change this to, let's say, 4, so that was that line 4 that is plotted. So now we'll go ahead and remove that. And additionally, let's label the x and y axis. Plt dot x label, these are the coefficients. So this is the sum of absolute coefficients And if you remember, this is also would then be the L1 norm, because we are just taking the sum of absolute coefficients. And then for the y, lt dot y label, so these are coefficients for each of those variables. So the number of lines is equal to number of features. So there are 10 lines here, and we can also plot which feature each line indicates. Uh, Here, what I want to point out is that as we start from 0 and move across this chart from left to right, uh, some features, uh, the coefficients of associated with some of the features become non-zero almost immediately. So here two features have become non-zero coefficients, and then as the regression continues, we can see other features become non-zero as well, and towards the end of the regression. So that's, and the shape of these lines tells how the regression proceeds. For example, for this particular green line, the the coefficient starts with 0 and then it increases, and then after it reaches certain value, it stabilizes at that point. It doesn't increase further, and same is the case with this particular uh, feature. However, in this feature, the coefficient becomes non-zero, it becomes negative, and it continues to decrease as the alpha value changes. Now let's look at a couple more variations. So the first item we'll look at is Lars path, and let's type that here, Lars underscore path. And for this one, we again can write the same method. So instead of just one variable, it returns 3. So we'll specify all those active and C for coefficient linear underscore model dot Lars underscore path, and here we'll specify the x, let's see, x and y that we have above, and method is equal to LAR. Now when we look at the shape of C, C is a 10 by 11 matrix, and we can therefore calculate the sum as we did before. Sum of absolute of C and axis is equal to 0. Then we can plot this plt dot plot C sum and then transfers of this, and this is the plot we get. Now let's create a plot for lasso. What we'll do is we'll create plots for lasso, LassoLars, and ridge, and then and Lars as we have already done, and then we'll compare all of them in just one plot. So let's why don't we just start with lasso, and here we have reg under, so we can get the coefficients. So I'm going to use a shortcut way here. So we need the coefficients L lasso, so C underscore lasso is our variable, and because this does not have the underscore coef underscore path underscore attribute, we have to do this manually. So I'm going to use the for loop using list comprehension. So for, and we already know the alphas that were created above, so we'll use the same alpha values. So here we have these alphas created, and we'll use the same alphas right here. So alphas, so these are the alphas we'll use. For A in alphas, what we are going to do is use linear underscore model dot lasso, and alpha is equal to A dot fit, and this fit is on x and y, and then we get the coefficients using dot coef, and all of this can be put in an array. So I'll type np.array, and thus when we look at the final output shape of this one, shape, we get Lasso, forgot the O, and we get 11 by 10. So we have 10 features. So as compared to our earlier coefficient feature, here we have a flipped version where the alphas are along the rows. So now when we get the sum, c sum underscore lasso, the alphas are along the rows. So when we take the sum np dot sum abs of c underscore lasso, here for axis we need to specify 1. So when we then look at the c and c sum underscore lasso dot shape, we see that it is 11. So for each of the alpha value there are coefficients calculated, and we have the sum of those coefficients uh, for each set. And now we can plot that. So plt dot plot c sum underscore lasso, and then we have c underscore lasso, and this should work. Yes, and this is the plot we get. Similar to this, we will go ahead and plot the ridge as well. So why don't we copy this entire code and paste it here. So this is for ridge, and the only change we are going to make here is type remove lasso and just type ridge there, and this would then become ridge, and this would become ridge, and we get the same shape. And again I'm going to copy this code right here and paste it here. We have, instead of lasso we have ridge, and again here instead of lasso we have ridge, and here instead of lasso we have ridge. So a ridge, and when we have 11. So now when we try to plot this, plt dot plot c sum underscore ridge comma c underscore ridge, and we don't need the transpose. So here as you can see, this does not start from 0, and to make that happen we'll have to add a 0 there. So to do that, what we'll do is create patch it with a row of zeros, np dot concatenate, and within a list we are going to specify np dot zeros, and this will be 10 zeros. And here then we use c ridge, that's there, and we are going to concatenate along axis 0. So we are adding another row of zeros. Concatenate, and here data type is not understood. So let's see, that is because the zeros takes a tuple, and we have now 12, and here we have 12. Now this is the output we get, so that is good. Now in addition to this, I'll come to the discussion of these once we create the subplots. So before we do that, let's go ahead and plot lasso Lars as well. So for this one we create another the LassoLars. So ll is equal to np. So this again is list comprehension. So for a in alphas, and here we have linear underscore model dot LassoLars, and alpha is equal to a dot fit x comma y and dot coef underscore, and then all of this becomes an array, np dot array. And we can also look at the shape of this one, is the same shape. Now we can get the sum c sum underscore ll is equal to np dot sum. We take the absolute value of these coefficients, and then sum it along the axis 1, because we know that the alphas are along the rows right here. And then we can go ahead and plot this. Plt dot plot c sum underscore ll, c underscore ll, and as you can see this is the plot we get. So we can now combine all these plots together. So to do that, we'll create a figure with subplots. So figure fig is equal to plt dot figure, and here figure size, fig size is equal to, within a tuple, let's specify 15 and 8, and number of rows, number of columns is equal to, we're going to 2 by 3 grid. Plt dot subplot nr nc, and this is the first plot, so 1. Plt dot plot see sum. Let's see what we had for lasso. For Lars we had c and c sum, so let's use that. So c sum, and we have c dot t, and then the next one is plt dot subplot nr nc. Let's copy this, so that would be much faster. Copy paste, and this is going to be the next one. Will plot lasso, so c sum underscore lasso, I think that's what we used, ridge, and c sum underscore lasso, and this was c underscore lasso. Let's see how we can plot these. C underscore lasso, yes, so that's good. C sum and c underscore lasso, so we should see 2 plots here. Okay, so that's good. Then why don't we add labels as well along with dotted lines. Y min y max is equal to plt dot y limit, and then plt dot v lines, and here we specify c sum, then y min y max, and line style is equal to dotted, and we have alpha is equal to 0.25, and plt dot title, this is LARS. So let's copy this and again paste it here. So this is lasso, and it had similar to this. Now we can go ahead and create another plot, which is be the third plot, and this will create the ridge here. So I'm going to remove that, add ridge, and this would be ridge. And finally we have the fourth plot there, which is the LassoLars. So change that, and this is just LL for LassoLars, and this is okay, there's one mistake I was doing. This should be lasso, and because we are using the y lim there, and this again should be, this should be ridge, and then this should be here we are using lasso lars, and that's that. So now if we do plt dot height underscore layout plt dot show, let's check this code again. We have c sum and c transpose, that's what we have, and that's Lars. Then for lasso we have these two, then we have the lasso here and lasso. For ridge we have ridge, and then we have c sum ridge, and we have ridge. And then for lasso Lars we have ll, so these are there, and then we have this one. So now let's go ahead and plot this. Awesome. So these are the plots we see, and there's no x-axis or y-axis, but these are the summed up values for the coefficients. So if the coefficient is b1 for this feature, then this is how b1 is evolving over different values of alpha. Now the biggest difference in these in all these plots is how ridge works and how lasso or these work. In ridge, all the elements become non-zero almost immediately, or most of the elements become non-zero almost instantly. The very first case here, we can see by 1,000, all of them are non-zero. And in this case, Lasso or Lars, we see that only two elements become first one element is non-zero, then the second becomes non-zero, and then the third, and so on. So there are a bunch of elements that are still zero, as these are there's these coefficients of these features becomes non-zero. So, and next point to remember is that the Lars and Lasso, they are very close. If we look at the paths they take, they are very, very close, and that's seen as a plus point when we are doing when either of these methods is used. So Lars is faster and it performs the same way as Lasso does, which is shown here. And this is the modification which is LassoLars. It also gives the similar output as we see for the coefficients. They look the paths look pretty close. They are very similar. So that was it for this video. I hope in this and previous video you got an intuition about what is least angle regression and how the paths for the coefficients as they evolve for different alpha, how they compare between Lasso, Ridge, LassoLars, and Lars. If you have any questions or comments, please let me know in the comments section below. I hope to see you all in the next video. Please like, share, and subscribe. Thank you.